So this is part of our ongoing section of physics, heat and thermodynamics, which is in your module 3, as you know. So last time in calorimetry, what we had understood is that if you look at the graph of temperature versus heat supplied to a material, while it is undergoing such a change wherein only its temperature is changing, its state is not changing. Okay. This is the type of graph that we get. That is, heat supplied is directly proportional to temperature change. Okay. For heating of a material, unless it undergoes state change. Now today we'll also understand about state change. Yeah, so unless it undergoes state change, this is the relationship between heat supplied and temperature change. And further, we had seen that this relationship was having an exact formula. That is, for example, if this is a solid material, not undergoing a state change, the exact relationship between the temperature change and amount of heat supplied is this, where M is mass, S is called the specific heat capacity. So in SI unit, it will be expressed in joules per kilogram Kelvin, or it can also be expressed in joules per gram degree C, or it can also be expressed in calories per gram degree C, whereas this will be in kilograms or grams or whatever. And delta T is the temperature change in Kelvin or degree C, and delta Q is the heat exchange in joules or calories. Right, so this is the general idea. Okay. Now, next thing we'll see. So this you've already seen in the last lecture, so don't need to write it down again. Now we'll also see the next thing, that if the material, for example, the solid is heated until it reaches a specific temperature called melting point, then further heat supplied at the temperature equal to melting point results in state change, okay, from solid to liquid. Okay. Likewise, when a liquid is heated, until it reaches its boiling point. Then further heat supplied at a temperature equal to the boiling point results in state change from liquid to vapor. So this aspect of heat exchange we can look at like this, that now for example if we start with a solid material, so initially the solid is undergoing heating, so the temperature is rising with the amount of heat supplied, but at a certain stage we will reach a temperature called the melting point. So the moment the melting point is reached, further heat supplied will now result in the process of melting the solid into liquid. So that is the state change. So during that state change, what will happen? The heat supplied will result in state change without the temperature changing. So during the second part of the process, there is melting occurring from solid to liquid. Now once all the solid is converted to liquid, again the liquid's temperature starts to rise with the heat supplied through a linear graph. But next, at a certain temperature, which is called the boiling point for the given liquid, when the temperature reaches that value of the boiling point, now further heat supplied results in conversion from liquid to gas, which is the process which we call boiling. And finally, when all the liquid is converted to gas, then further the gas's temperature will increase again. So once this boiling process is completed, we are in the gaseous phase. Before that, the material was in liquid phase. Yeah, this part you have to write down. Okay. So you give it the heading of state change and something called latent heat. So we'll come to what latent heat is in just a moment, but first we just note down this section. Okay, so now next thing we'll understand here, the concept of latent heat. Just a- yeah, I shall scroll up and finish writing this down first. Okay, so next we'll see the definition of latent heat. Okay, so during state change, whether we are talking about melting or boiling, whichever of the two, okay, the temperature remains constant. That is temperature equal to melting point or temperature equal to boiling point till all the material has undergone the state change. So, for example, if you have a certain mass of ice and it's reached 0 degrees C, now at 0 degrees C, when you supply the heat, first all the ice has to melt, and only the temperature will increase from 0 degrees C after all the ice has melted into water. It will not happen that part of the ice has melted into water and the temperature starts increasing. Until the melting process is 100% complete and you have no ice left, you have only water. Until that time, the temperature will remain constant at 0 degrees C. That is what we mean by saying that the temperature remains constant till the material has undergone the state change completely. Okay. And the relationship is that the heat required for state change is equal to the mass of material multiplied by a quantity called specific, called latent heat. So the heat needed to change the state of m mass. M is the mass of material undergoing a state change, and L is latent heat. It is measured in joules per kilogram or calories per gram. Yes, they are interrelated, so that's how. Okay, understood. Akash? So just note down this definition, then we'll understand with an example. So because the temperature remains constant, so there is no relationship between Q and temperature during the state change. The relationship is mass of the material into the amount of heat required per unit mass for state change. So latent heat is the heat needed per unit mass change in state. Okay. That's another way to understand the definition of latent heat. Okay, so let us understand this with an example. So like specific heat capacity, latent heat is also material property. So in fact, we define two types of latent heat. Latent heat of fusion, that is the heat needed per unit mass for melting, that is solid to liquid. And further, we define latent heat of vaporization. So this is the heat needed per unit mass for boiling, that is liquid to vapor. Fusion is actually the reverse of melting. Fusion is the process of liquid to solid. So yeah, I'll go back to the last line, don't worry. But for example, latent heat of fusion for ice is about 80 calories per gram. So this means that to melt 1 gram of ice to water, okay, of course the melting point is 0 degrees C. At 0 degrees C, 80 calories of heat has to be supplied to the ice. On the other hand, or we can say that to fuse or solidify 1 gram of water at 0 degrees C into ice, okay, 80 calories of heat has to be absorbed, because that's the reverse process. So to solidify the liquid into solid state, we have to absorb heat from it. So 80 calories of heat has to be absorbed from the water, so it will convert to ice. Similarly, latent heat of vaporization of steam is approximately 540 calories per gram. So to vaporize 1 gram of water, at 100 degrees C, 540 into steam, that is, okay, into steam, 540 calories of heat has to be supplied to the water. Okay. So this is a more specific meaning of latent heat. So just make a note of this section also. Yeah, so just take down this example. Okay, so now let us understand an example which involves both temperature change and state change. So, for example, we have a situation like this, that a container is filled with, let's say, 20 grams of ice at minus 5 degrees C, okay, and left exposed to atmospheric air at 25 degrees C. So, after a sufficiently long time, what we observe is that the ice has melted, okay, and the water formed has heated up to 25 degrees. So calculate the amount of heat absorbed by the ice from the atmosphere around. Okay. So for this, the data given to us is that specific heat capacity of ice is 0.6 calories per gram degree C. Latent heat of fusion for ice is 80 calories per gram, and specific heat capacity of water is 1 calorie per gram degree C. And also 1 calorie is equal to 4.18 joules. So just try out this question. So what you have to understand in the question is that first the ice is heating up from minus 5 degrees C to 0 degrees C. Okay. And then it's going to melt with further heat absorbed from ice at 0 degrees C to water at 0 degrees C. And then the water formed is going to heat up finally from 0 degrees C to 25 degrees C, further absorbing heat from the atmosphere around. So the total heat supplied by the atmosphere to the ice initially at minus 5 degrees C to come up to water at 25 degrees C, that we have to calculate. Okay, Kunj, I'm checking out your calculation now. So the total heat, let's say we are dividing it into three categories, Q1 plus Q2 plus Q3, where Q1 is the heat for ice at minus 5 degrees C to reach 0 degrees C. Then Q2 is for melting, and Q3 is for the heat for water to heat up from 0 degrees C to 25 degrees. So let's calculate each one of these. So Q1 will be M into specific heat capacity of ice into this first temperature change. So we have 20 grams of ice into 0.6 calories per gram degree C into a 5-degree change. So that you will see will become 100 into zero point 0.6. So that is 60 calories. Okay. Then Q2 will be M into latent heat of fusion for ice. So that will be 20 grams multiplied with 80 calories per gram. So that's 1600 calories. And finally, Q3 will be M into specific heat capacity of water into temperature change in this third process. So that is 20 grams into 1 calorie per gram degree C into 25 degrees C. So this will become 500 calories. So the total Q will become 60 plus, sorry, 60 plus 1600 plus 500. So that's how much now? 2160 calories, or you can say 2.16 kilocalories. And if you like, you can convert that to joules by multiplying with 4.18. So could just check out your calculation and see how to go about this whole thing. Okay, so that's fine. So anyway, I hope this question is clear. And the concept of the calculation of both specific heat capacity based, heat absorbed or heat supplied, etc., as well as latent heat based calculations, they're both clear. Okay. Now, from this, we move on to what is called the principle of calorimetry. So, the principle of calorimetry actually applies to a particular apparatus called calorimeter. So, a calorimeter is an apparatus used to measure heat exchange. Okay. So, it consists of a vacuum sealed heat insulated vessel, okay, which can be filled with different materials at different temperatures, okay, which eventually exchange heat with each other and reach a final, what we call, equilibrium state. So let's understand the definition of this term equilibrium state. Thermal equilibrium is a state in which a mixture of materials exists at a common uniform temperature, okay, which we can call the equilibrium temperature, and no heat exchange takes place between them. So basically, when a mixture of materials is in this equilibrium state, that is, they are at a common uniform equilibrium temperature, then there won't be any heat exchange taking place. Whereas if we have a mixture of materials which are not in the equilibrium state, that means the temperature is not same for all of them or not uniform throughout the mixture, then heat exchange will take place till what happens? Till the equilibrium state is reached. So that is what the principle of calorimetry is all about. And this kind of a heat exchange experiment is carried out in the particular apparatus which is called the calorimeter. So just make a note of this section quickly first, then we'll discuss further. Yeah, we will understand about the calorimeter and the principle of calorimetry in more detail. So you can just think of the calorimeter like a flask, like a thermally insulated flask, and the thermal insulation is actually achieved by making it a double walled flask which is vacuum sealed. So between the two walls there is vacuum sealing. So double walled vacuum sealed flask kind of thing it is. So there is no heat exchange between the inside and outside. Okay, so that is the calorimeter. So inside it, initially, if we keep some material which is at lower temperature, mixed with another material which is at higher temperature. So what will happen? Initially, T1 is less than T2. So heat exchange takes place. Okay, the material at higher temperature T2 supplies heat to the material at lower temperature T1, which absorbs this heat. Okay, and this process of heat exchange continues till thermal equilibrium is established. So at a uniform final temperature, let's say T. So the material at T2 cools down from T2 to this final temperature T. So obviously this final temperature will be less than T2 but greater than T1. So the material at higher temperature cools down to T and the material at lower temperature heats up to T. And in the process, what the principle of calorimetry tells us is that the net heat supplied by the material cooling down will be equal to the net heat absorbed by the material which is increasing in temperature. So we'll just write down the definition next, but it's very logical to understand that because it's a vacuum sealed or heat insulated container, there's no heat exchange with the surrounding. That means the heat exchange is only happening between the materials which are inside the calorimeter or inside the flask. So whichever material is lowering its temperature, it is losing heat, and the other material which is raised in temperature, that is absorbing that much heat. So the heat supplied by the material which is cooling down must exactly be equal to the heat absorbed by the material which is heating up. So that is the principle of calorimetry. Okay, so next up, the principle of calorimetry. That is the heat supplied by the material or materials cooling down must be equal to the heat absorbed by the material or materials heating up. Okay. From the initial state to the final thermal equilibrium state. So let's understand this with an example. 100 grams of water at 10 degrees C are placed inside an insulated vessel or a calorimeter. Okay. Now, a metallic block of mass m, specific heat capacity 0.2 calories per gram degree C, okay, is placed inside at initial temperature of 45 degrees C. If the final equilibrium temperature is 25 degrees C and given the specific heat capacity of water equals 1 calorie per gram degree C, then find the value of m, that is the mass of the block that we have to find out. My mass of the metallic block, which is made of the material which has specific heat capacity of 0.2 calories per gram degrees. And initially the metallic block was at 45 degrees C, whereas the water was at 0 degrees C. Whereas after a long time, when equilibrium is reached, the common temperature of the mixture becomes 25 degrees C. So the equilibrium temperature they reach is 25 degrees C. So from all this information given, we have to find the mass of the metallic block. Let's try this question out. You have to just apply the concept we have written down above, which is the principle of calorimetry. Okay, so let's calculate the value. So we can see that in this question you have 20 grams of water that is heating up from 10 degrees C to 25 degrees C. Sorry, 100 grams of water, not 20 grams. And you have m grams of metal which is cooling down from 45 degrees C to 25 degrees C. So the heat absorbed by the water will become mass of water into specific heat capacity of water into temperature change for water. So that is 100 grams multiplied with 1 calorie per gram degree C multiplied by the temperature change of 15 degrees C. So that is 150 calories. That is the heat that is absorbed by the water. Now the heat supplied by the metal, that is a mass of metal into specific heat capacity of metal into temperature change for metal. So the mass is unknown, but the specific heat capacity was 0.2 calories per gram degree C. Into the temperature change, as you can see, is going from 45 to 25, so it's decreasing by 20 degrees C. So 4 calories. So the heat supplied must be equal to the heat absorbed. This is the principle of calorimetry. So 4 calories must be equal to 150 calories. So this is the answer for this question. It's basically a very simple type of question. Just try to understand how we are doing this. Go through the steps and let me know if there are any doubts. Okay, so hope this is clear. Now we move on to another type of question which is a little bit more difficult than this one, because there will be a state change involved. So suppose we have a situation like this. We have 20 grams of ice at 0 degrees C are mixed with 100 grams of water at 60 degrees C. At 15 degrees C. So in a calorimeter. Latent heat of fusion for ice is given 80 calories per gram, and specific heat capacity of water, standard value 1 calorie per gram degree C. You have to find the final equilibrium temperature of the mixture. Okay, just try this out. So again, it is the ice that will be absorbing heat, and the water which is initially at 15 degrees C, which will be supplying the heat. Okay. So water will be cooling down, ice will be first absorbing heat to melt, and then if the temperature rises, then absorbing further heat for the temperature to rise from 0 degrees C to whatever final temperature. So we have to find that final temperature. Okay, anybody got the answer for this? Now see, in this thing, what is happening is that the 20 grams of ice at 0 degrees C, let's say Q1 is the heat needed to melt all the ice. So Q1 is going to be how much? It's going to be 80 into latent heat of ice. Sorry, 20 into latent heat of ice. Mass of ice into latent heat of ice. So that's going to be 20 into 80 or 1600 calories. Okay. Whereas the maximum heat that the water can supply, let's say that it's Q2, that is mass of water into specific heat capacity of water into maximum temperature change that the water can undergo. Now this maximum temperature change will be how much? It will be 15 degrees C if the final temperature is 0 degrees C. Because if the final temperature is greater than 0 degrees C, if final temperature is greater than 0, then delta T will be less than 15. Okay. So the maximum heat that is available to us from the water, this is, we have 100 grams of water at 15 degrees C. So 100 into 1 into 15. So 1500 calories. This is the maximum available heat from the water. The water cannot give you more heat than 1500 calories because the temperature of the water cannot come down to anything below 0 degrees C. So therefore you can see that Q1 is greater than Q2. The heat required to melt all the ice is more than the heat available, the maximum heat available from the water. So this should give you a hint about what the final temperature is. Just go through this and try to interpret and tell me the answer that what should be the final temperature then. So basically my final statement should be like this, that since Q1 is greater than Q2, therefore the final temperature. So what can we say about the final temperature? Just try to think of this logically. First go through the calculation of Q1 and Q2, make sure you understand that. And then when you can see Q1 is greater than Q2, try to figure out what the final temperature should be. Yes, very good. The final temperature, Kunj, that's correct, will be 0 degrees C. No, Rupesh, the final temperature will be 0 degrees C, because see what is happening is now that, okay, Q2 will be the heat supplied by the water, and that will be equal to 1500 calories. Okay, and only a fraction of the total ice will melt. Okay, so if the mass of ice melted is x grams, that means x multiplied by latent of heat of ice should be equal to Q2. So x multiplied by 80 should be equal to 1500. So x will be equal to, or 150 by 8, so that is 75 by 4, or okay, so only x equal to 18.75 grams of ice will melt. Okay. So basically what is happening is, because Q1 is greater than Q2, therefore all the ice cannot melt. And finally, this is showing us that out of 20 grams of ice, okay, only 18.75 grams will melt, and 1.25 grams remains in ice state, okay, at the final temperature of 0 degrees. Excuse me. Okay, so people hope this calculation is clear. Yeah, good, Rupesh. Okay. So with this, we complete this section of calorimetry. It's a very small chapter, the two definitions of latent heat and specific heat capacity. Maybe in the beginning of the next lecture, we'll do one or two more questions from the module for this. But next lecture, we will basically be starting with kinetic theory of gases, which will be the next subtopic within heat and thermodynamics. So kinetic theory of gases, part of which you might have studied in chemistry also. That is the next aspect that we will study. Okay. So that's it for today's session, people. Wish you all the best.